we have Victor Chan presenting for us. He's a PhD candidate in the Department of Astronomy and Astrophysics, and he's talking about the expanding tension in modern astronomy. In his spare time, Victor likes to nap, play RPG video games, and talk about how much he wants a cat. So please join me in welcoming Victor. Woo!
Thank you, Taylor. Yeah, so I think the first thing I want to say or to do is explain what I mean exactly by the expanding tension in modern astronomy. And to do that, I think the best way to do that is to reintroduce myself. I am an astronomer, but more specifically, I would call myself a cosmologist. And what that exactly means is that when I come into work every day and do my research, the questions that I try to answer generally pertain to answering questions that we have about the origin and evolution of the universe. And one of the biggest topics in cosmology right now has to do with what we call the Hubble Constant. And what the Hubble Constant is a number that describes the rate of expansion of the universe. Now that's a lot to take in, and I'll be talking about exactly what that means. But for now, what I want you to take into account, take out of this statement is that we have, as good scientists, we design multiple experiments to measure the same value, just so we can cross-check our data and ensure that we're doing a good job. But for this Hubble constant, we measured two values that are distinct from one another and they don't quite agree. And this is what comes about, what generates what we call a tension in astronomy. So this is a hot topic enough that the press generates a lot of headlines about this. Cosmologists debate how fast the universe is expanding. Tension over Hubble constant continues, and my favorite, Hubble tension headache. Clashing measurements make the universe's expansion a lingering mystery. This is actually a very ongoing topic. This is a conference that happened just that I participated in, where the world's leading astronomers in this topic got together and tried to talk about what the heck is actually going on. At this conference, we had a dedicated hashtag that you can't see on the board here, but I've rewritten here. It's called KITP, which is the name of the institute that we had it, and then called Hot Takes. So people were tweeting exactly what they were thinking about it during this conference. And during this conference, we had a lot of fun. We even upgraded this situation from a tension to what we call a crisis now. And you can see people are having a lot of fun with this right now. But really what this all boils down to is fundamental questions in science, such as how do we know when we're right about something? And when do we actually say that we fully understand a topic? Okay, so these are things that I want you to think about. Yeah, so let's just get started for me to explain what exactly I mean by when I say that the universe is expanding. Okay, so let's get our bearings here in our place in the universe. This is home, this is Earth. We live on a planet that orbits around a star that we call the sun. Our sun is a star. It's one of many stars. Our sun lives in a galaxy called the Milky Way. A galaxy is a collection of many stars. The Milky Way in particular is a collection of billions upon billions of stars. This is an artist's rendition of the Milky Way because we can't actually get out of the Milky Way and take a picture of it, but this is what we imagine the Milky Way looks like if someone else were to observe it. And I've placed the picture of the sun roughly where we think we are in the Milky Way. And the Milky Way is not the only galaxy in the universe. There are other galaxies around us, such as the Magellanic Clouds, the small and the large one, and also the Andromeda Galaxy that is nearby. And the Andromeda Galaxy also has satellite galaxies orbiting around it. And the fun thing about all of these galaxies is that they are gravitationally interacting with each other. They pull and tug on each other while they orbit, while they move around in the universe. But there are other galaxies that are further away that aren't part of this local group of galaxies. And these are the distant galaxies that I'll be talking to you about today. These galaxies don't interact with us gravitationally because they're way too far. Yes, of course I could do that. I could also speak a little bit louder if that would help. I should have asked first, I'm sorry. Okay, so pertaining to these galaxies in question, I want to ask a sort of rhetorical question. How far away are these galaxies? What do you guys think? It's a rhetorical question, so I won't be taking answers. I'm sorry. The answer is I don't know, because these galaxies are over there, and I can't take a ruler and measure how far these galaxies are because they're really far away from us. But scientists are clever, and we can think of ways to measure distances to faraway cosmic objects. But before we start measuring distances to faraway galaxies, let's think about how far away stars are. In particular, there are many ways to measure distances to stars, but the most, I guess, one of the most prominent ones in astronomy today is something called the parallax method. And to explain this, I'm going to use an example that is a bit closer to home. So imagine you're on a road trip, driving along the highway, and you see a mountain in the distance. Along the way, you see a tree, and you're driving past it. And before you drive past this tree, you look at it, and you see that the tree is on the right side of this mountain from your point of view. A couple of minutes pass, and you drive past the tree, and now you're looking back at it, and now you observe the tree to be on the left-hand side of the mountain. This shift in the apparent position of this tree is what we call the parallax effect. And the larger the shift means that the closer the tree is to you. And the further away the tree is from you, you would see less of a shift in parallax. You can imagine doing the same thing as the Earth orbits around the sun. Say we orbit this star, we do orbit the sun, but say we observe the star at a certain time of the year, let's say now. We'll see it in some position of the sky, but say half a year passes. In the spring of next year, we'll see the star in a different position of the sky relative to its background. And you can imagine that if the star was closer to us, you'd see a much bigger shift. Right, so the parallax effects means that you see at different times of the year that the star will be in one position of the sky that is different from the other one. And if the star was further away relative to its background, you would see a much smaller of a shift. And if the star was even further away, you would see a much smaller shift. Until you get even further yet, you won't be able to observe much of a shift at all. So the parallax effect only takes us about as far as we can observe as well as we can resolve the star. Okay, so just to reiterate, the parallax effect lets us observe stars that are about relatively near to us, so stars that are within our Milky Way. But that doesn't take us to my original question, is how far away are the galaxies, because those galaxies are much further away. To get distances that are much further away, so we don't know how far away these galaxies are still. To get even further distances, we understand what stars do. We understand that they're flaming balls of gas, and a lot of physicists over the years have figured out the evolution and life of these stars, exactly how they work. And there are special stars called Cepheid Stars that we can understand should radiate at a certain brightness. And every star that is a Cepheid type star, we imagine to have the same intrinsic brightness. So knowing that, if I have two stars in the night sky and I tell you that they share the same original brightness, which one do you think is further away? Just point with your finger, or put up the hand that is on that side. So this one that's glowing brighter should be the one that's closer away. And you can imagine that if I had a candle, holding a candle closer to you, and I move it further away, the further I move, the dimmer that candle would be. So that's exactly what we do, is we first take parallax measurements of stars that we understand to have the same intrinsic brightness. And then once we observe stars in galaxies where we can't observe parallax anymore, we can use these special stars that we understand the brightness of to estimate how far away these galaxies are. So that gets us to nearby galaxies, but these Cepheid stars, these standardizable candles, can't be resolved in extremely distant galaxies, like the ones that I'm asking you to tell me the distance of. To get the distances to those galaxies, we need to study another phenomenon that in relatively nearby galaxies, say we have a galaxy here that has a Cepheid star like I have showed you before. Once in a while in this galaxy, we'll see a distant explosion. This is a supernova explosion caused by the death of dying stars. They blow up and they glow really bright, but they don't look like this kind of explosion. What we see in our camera actually looks more like this. It's just a white dot. So I'll just step through that, like that. It looks like that. And it's a little silly to think that a white dot can tell us anything, but this dot is extremely bright. Sometimes they can outshine even the entire galaxy. But it really is just a dot that tells us how bright, that tells us how far away these galaxies are, because we think very special types of supernovae blow up and radiate with relatively the same brightnesses. So if we can use these Cepheids to calibrate yet again how bright these supernovae are, we can actually get distances to really far galaxies if once in a while we see that there's an explosion in one of them, like this one here. So this is just to reiterate what I've talked about so far. First, we use the parallax effect to calibrate the distances to these special Cepheid stars, the brightnesses of these special Cepheid stars. Then we use the... Okay. Okay, then we use the Cepheid stars to calibrate how bright the supernovae are. And then once we understand how bright supernovae are, we can look at very distant galaxies and measure their distances. And that's this last step of what we call the distance ladder. So it's kind of a ladder where you build up from closer distances to further and further distances away from you. And that's how astronomers measure distances to cosmic objects. And this is something that was done by someone called Edwin Hubble. Here he is smoking a pipe and looking rather dapper. And what he was interested in is this final step of the distance ladder. Because what he did was when he looked out into the universe and looked at faraway galaxies, he found that galaxies tend to look redder than he expected. And scientists understand, or physicists know, that if something is redder than you generally would expect, that tends to mean that it's moving away from you. And what he found is that the further a galaxy was from us, the faster it was moving away from us. So like a good scientist, he puts all of his data together into a graph that looks like this. Okay, so the further away a galaxy is, the farther away it moves from us. And he found that the trend tend to follow roughly a line. And this line is exactly what we call the Hubble Law. And it's the slope of this line that tells us that we call the Hubble Constant, and it tells us the expansion rate of the universe. Okay, so what Edwin Hubble originally measured in 1929 was that the Hubble constant was 500 kilometers per second per megaparsec. And that's a really weird number to imagine, so let's step through it together. A megaparsec is a measure of distance, and it's roughly equal to 30 billion kilometers. So imagine a billion kilometers, and now imagine 30 billion of those. That's what a megaparsec is, okay? Yeah, space is huge. So what this Hubble constant is telling us is that if we observed a galaxy that was 1 megaparsec away, then Edwin Hubble tells us that this galaxy is moving roughly 500 kilometers per second away from us. That's really fast. And if it was 2 megaparsecs away, it would be moving away at 1,000 kilometers per second, and so on. Okay, so I said that galaxies moving away from us means that the universe is expanding, but I didn't really argue why that was. Like, there could be any explanation as to why that is. But really, that is the easiest explanation to why we observe every galaxy moving away from us. It's not that we smell or anything, but I can explain why that is using a bit of a philosophical argument, something called the Cosmological Principle. And that states that the universe is homogeneous and isotropic. So let's break that down. Homogeneous means that the universe is the same everywhere. It doesn't matter if I'm here or in the Andromeda galaxy or in one of the other distant galaxies that I was talking about. Isotropic means that the universe looks the same no matter what direction I'm looking at. It doesn't matter if I'm looking this way, that way, doesn't matter. So to put that in plain English, that just means that there are no special places in the universe. But hold on. I live on Earth, and I know that this statement really isn't that true, because if I'm here, things don't look the same as if I'm over here. I look here, I see someone different than someone over there. So how would this be true? So that's what the star actually is here for. This statement is true at the largest scales of the universe. If you zoom out far enough, then it generally is true that the universe is homogeneous and isotropic. And that generally logically follows that there are no special places in the universe. So we don't live in a special part of the universe. Does everyone still hear me fine? Okay, so if you believe the cosmological principle, then the easiest explanation why the galaxy we observe is moving away from us, or every faraway galaxy is moving away from us, is that space itself is expanding. So I'm showing a cartoon here where these stars represent galaxies, you can imagine, and the grid itself is expanding. So if you pick any one of these stars and you look out at a different star, so I'm going to pick this one, then that star is moving away moving away from you. And the further the point on further the stars that you choose to look at away from you, the faster it's moving away from you. So you look at that for a bit. Try to. Okay. So if we generally now believe that the universe is expanding now, then you can imagine that you can just turn time back. And as you go back in time, things used to be closer together and closer together and closer together. If you go far enough back, things get closer and closer enough together until they become a really hot and dense state. And that's what we call the Big Bang. And this was theorized way before Edwin Hubble observed the expansion of the universe. So the Hubble Law is a piece of evidence that supports the Big Bang. Okay, so the Big Bang was really hot and happened a long time ago. And we know that hot things emit light. So can we look back and examine the light that happened from the Big Bang? The answer is yes, but it's a little hard to imagine exactly why we can do that until you realize that light travels at a finite speed. It travels at the speed of light, which probably doesn't mean much to many people, but the takeaway from there is that the further away an object is, the light that is going into my eyes was emitted further in the past. So if you can look really, really far away, you can look really, really far into the past. And the furthest point that we can look in the universe actually emits something called microwave light, and it looks something like this. This is the cosmic microwave background. Yeah, it looks really boring, doesn't it? This is a large part of my PhD research. But I don't study just a white blob, okay? If I turn up the contrast, now this is a contrast of 1 in 100,000, then we can see that there are actually features in the cosmic microwave background. Does anyone see anything special in this cosmic microwave background? It really should just look like random blobs to you, really nothing special. But these random blobs are actually very significant to us, and I'll explain why that is in a second. But I want to show you just how smooth the cosmic microwave background is, because it's a really stark difference to go from this and this, and it's hard to understand how big of a contrast 1 in 100,000 is. This is a cue ball. If you've played pool before, you may have probably seen one of these. The World Pool Billiard Association has standards for how round a pool ball should be. It puts it at 2.25 inches with a tolerance of 0.005 inches. So a pool ball has a standard pool ball has contrast in its roundness of 2 in 1,000. So compare that to the cosmic microwave background. This thing is 500 times smoother than this pool ball. Okay? So these features are actually tiny. Okay, so like a good scientist, we like to study the map of the CMB, but these blobs actually don't really mean that much to us because they're really effective. But we care about how many there are and how bright they are. So what we do is we take statistics of this map and then we plot them. So what we do is we care about how big these blobs are and how many times they appear and also how bright they appear. So how many times and how bright they appear relates to what I'm calling the significance of the blobs. And here they are plotted to their angular size, so how big they look on the sky. So bigger things are on this side of the plot, and smaller things are on this side. And the key takeaway I want to show you from this plot is that we use only 6 numbers to describe this squiggly line. So the dots come from the data itself, and this line is a theory line that we create with just 6 numbers, 6 free numbers. And just to show you how amazing that is, I'm going to dig up some past drama for some of you. This is some high school math. So this is a slope, and this is a line, and we know that the equation of the line you can describe with a slope and an intercept. So that's 2 numbers that are needed to describe a straight line. This is a parabola. And the quadratic equation tells us that we need 3 numbers to describe a curvy line like this. So we can make a line more complex by adding more and more numbers to it. But we only need 6 numbers to describe this line with so many curves and wiggles in it. There are like 8 bumps in here. 6 numbers really isn't that, is a really a really small amount of numbers to describe it. And the reason why it describes this curve so well is because we understand physics and we can build a theory for that puts together equations that use the numbers more efficiently and describe something like this. But the crazy thing isn't that this line matches the data really well for the CMB. These 6 numbers also describe most of the evolution of the universe. They describe the formations of galaxies and stars to pretty high degree of accuracy. Yeah. So the next thing I want to tell you guys about is the fact that these blobs are actually related to the galaxies that I was showing you earlier. These blobs are related to tiny little overdensities, in contrast about the order that I was telling you about, 1 in 100,000. These blobs represent little tiny overdensities or underdensities in the universe. There's just a tiny bit more stuff in the red parts than there are in the blue parts, just a tiny bit. And over time, the parts of the universe with more stuff generally pull on each other with gravity and they start to collapse. And eventually, it's these blobs that eventually become the galaxies that we see today. It's not the same ones because these are the really old ones that are really far away and they haven't collapsed yet at the time that they emitted the light that we observe. But eventually they will become galaxies like the ones we observe today. And you can imagine doing something similar with these galaxies. These galaxies probably have some characteristic separation between them or apparent separation between them. Right, so billions of years later, these little patches become something like this. And you can think about relating the distances of these galaxies together, kind of like this. So the universe doesn't look like this, the galaxies don't look like this, but this is a kind of a depiction of what we might think about doing when I'm talking about looking for the characteristic or typical separation between galaxies. But wait a minute, these two are just the same thing. Because we're comparing blobs of a characteristic size to separations of things in the sky of a characteristic size. And the only difference between these two things is that these blobs have collapsed into the galaxies and that the universe has expanded in that time. And the universe has expanded in that time. So this is an independent way of measuring the Hubble constant, which describes the expansion of the universe. So this is what we call the inverted distance ladder, but to avoid being confused with the actual distance ladder, I'm going to call it the CMB method experiment. So just to remind you, the distance ladder tells us building up close to far away that we see galaxies are moving further. And Edwin Hubble measured this number to be about 500 kilometers per megaparsec. This was 90 years ago. 90 years ago. Technology has improved significantly since then. Now the constant is probably closer to something like 10 per second per megaparsec. This gentleman is Adam Rees. He is a Nobel Prize winner, and he leads the SHOES collaboration, which does measurements of the Hubble constant using the distance ladder. So how does the CMB do? On the CMB side, the Planck collaboration runs a space satellite called the Planck satellite, which observes the CMB, and they find that the Hubble constant is something close to 68 kilometers per second per megaparsec. So if you look at these two numbers, they seem much closer together. They seem like they agree much better than Edwin Hubble did 90 years ago. But really, how do you compare how well these two are doing? But I've already spoiled the answer for you. But here's where I reveal that this talk isn't really about science. It's about errors and statistics. Okay, so taking a side break here, I want you guys to tell me how long this key is. Just take a minute, talk to your neighbor. Okay. Put your hand up if you think it's A. Put your hand up if you think it's B. How about C? and D. Okay. The thing about all of these answers is I included something called an error to them, and that's just because I really don't understand how long this key is based on this ruler. How do I actually draw a line from the tip to the ruler? I can't see where it's lined up. And I really can't either one, the errors kind of would account for each other. But now if I drew another line to draw the tip down to match it up, which one would you pick now? If I see this line now, I would probably pick C, because now I have much more information, and I can drive down my error, because now I understand that the tip of the key lines up with something that lines up just before the 3.1 mark centimeter. A bit of an error because I don't actually know how well I can eyeball this number. And it's these errors that are kind of the crux of modern physics. If you see a report of any measurement and it doesn't have an error associated with it, then it's garbage. Like, it's no joke. Like, if no one reports an error, no one will believe you. Like, how wrong are you? You can't just be perfectly right. No one will believe you. Okay? Okay, so that's what this is, what I showed in the beginning. So this is a comparison of the cosmic microwave background measurement. That's this vertical line and its error in the shaded in part. And this is from the distance ladder, this line, and its associated errors give it this shaded in area. And you can see now that if you take into account the errors that they report, they don't agree at all. What the heck is going on? Okay? So let me, the answer is that most of us actually don't know. And that's what's driving this controversial tensions. But I can step through and give you some examples of what might be going wrong. So when I explained parallax earlier, I made a very fundamental assumption that this star was stationary relative to the background. Say it was moving at some velocity, and I observed the position of the star now. When half a year passes, it would be moving. It would have moved to a different position on the sky, and I would measure a completely different parallax than I normally would have if the star was stationary. Our technology is advanced enough to take into account some of this effect, but it's still there, and it really will be there, no matter what you do. And it really depends on how well you can account for this kind of error. Oops. Okay, so that's one thing that you can come with. Could be a problem. But scientists are stupid. We know that this is a thing. Another thing is, I talked a lot about the intrinsic brightnesses of stars. In reality, when you observe a star, it doesn't look like this. You don't see a perfectly resolved star. There's stuff in the way. There's a lot of stuff in the way. There's a heck of a lot of stuff in the way. It's actually gross how much stuff there is in the way. Like, okay, and it obscures our view of these stars. But we do our best. We understand how dust works, how obscuring our view works, and we can do our best to clean out our measurements of these stars. But no matter what you do, these clouds will be there, and they will affect your measurement. So that's another problem. One more thing is the last step of the distance ladder in these supernovae explosions. I told you that we think that they are from the results of dying stars, but beyond that, there really isn't that much more we know about. There's a lot more we know about them, but with regards to how bright they should be, if anyone tells you that they understand them perfectly, they're lying to you, because it's probably one of the least understood areas in astrophysics right now. I don't say the most unknown area because there are a lot of weird things out there. Okay. And this comes into play in the distance ladder, especially this middle part here, when we're trying to calibrate how bright these supernovae are using the special Cepheid stars. If you look at this last panel here, there are so many points, so many galaxies with supernovae in them. And then in this middle one, how come there are only say around 10-ish points? And that's just because supernovae happen kind of randomly. We can't predict when a star is going to explode in a nearby galaxy. And we need them to be exploded in a near enough galaxy that we can observe these Cepheid stars in order to calibrate their brightnesses. And the truth of the matter is that there just haven't been that many for us to observe nearby to calibrate their brightnesses. And this is one of the main driving forces of the errors that we see in the distance ladder. Okay. moving on to the CME side, I said that we relate the blobs on this picture to the blobs in this picture, but we make a lot of fundamental assumptions about this as well. In particular, this is a very simplified picture. In reality, the galaxies look more like this. We don't see very clear-cut characteristic distances between these galaxies. What we can do is count lots and lots and lots of galaxies, and eventually all these numbers will even out, and we can get a typical separation between these galaxies. So it comes down to how many galaxies we can actually observe and relate their apparent distances from one another. Another thing is that this expansion of the universe is very heavily tied to our theories of the universe, or theories of the evolutions of the universe. And I told you that the main theory that we use in cosmology today relies on 6 parameters. There are many additions to this theory that keep adding on parameters and other weirdo things to the theory. And but yeah, there's a very fundamental assumption that you're making when you're making this measurement with the CMB that is tied to the theory. I'll come back to this in a second. But the final thing that we have to think about is how well do we actually trust our instruments? We take data in astronomy from telescopes, and at the end of the day, we have to really trust in the systematic errors that come from our telescopes and our instruments. And we have to really truly understand what the heck is going on to get the light that we're observing out in space into our machines and then into the numbers that we see on our computer, and then we plot them. There's a lot that goes on in order to get from the light to a number that we measure. And this is some people's entire PhDs is to figure out systematics of telescopes. Okay? This is probably the biggest problem that I would say contributing to the tension. Okay, so say you understand all of your errors, you think you understand all of your errors, you think you understand all of your systematics, and you think you understand your theory pretty well. What do you do next? This is where the fun begins. Not for me, but for the theorists. Okay, this is the archive. This is where physicists post their papers before publishing or after they publish, and it puts it in an open place for everyone to read. And I'll scroll through a few headlines for you that are pretty fun. Quintessence, axion, dark energy, and a solution to the Hubble tension. So I know exactly one person in this room understands this title perfectly, and I don't think anyone else does. I'm not the person who understands this title perfectly. Okay, here's another one. Rock and roll solutions to the Hubble tension. People are having an absolute ball with this thing. Gaia Cepheid parallaxes and, quote, local hole relieve H0 tension. Right? I'll actually talk about this one a little bit. Yeah, this one. So the local hole takes into account that we're observing this expansion of the universe, and it postulates that we're living in an underdense region of the universe. And what that would mean is that, to understand what that means, if we live in a very dense part of the universe, that means there's a lot of matter around us. And what matter tends to do is that it pulls on each other with gravity. If you've got a lot of things pulling each other together, you can imagine that space would have a harder time pulling you apart. Right? So now say you lived in an underdense part of the universe. Then I think you would have less matter around you that would pull on you less strongly, and then the universe expanding would pull you apart much faster. And that's one of the main arguments made by this paper to try to explain why the local distance ladder measures a much higher value of the Hubble constant. Because the local distance ladder measures a very high expansion rate of the universe. The problem with this is that to actually have such an underdense region of the universe to account for such a discrepancy in your measurements, you would have to live in an exceedingly special place in the universe. And I just said that the cosmological principle kind of forbids this. We have to be very arrogant to think that we live in such a special place to observe such a large underdensity. And there are a few people that feel very strongly about this kind of statement, and they put other papers back on the archive to refute this. 7 problems with the claims related to the Hubble tension in this paper. So this was put up. This is a public place. Yeah. So this was posted on, I think you can see here, October 7th, 2018. This paper was posted on this was October 6th, 2018. This was posted the next day. And a week later, the original team posts H0 tension response to this paper that is responding to their original paper. So this is really fun. I get to make memes about this. Like people are arguing about this. It's really fun. And I think the moral that I'm trying to show you is that it's weird that we're measuring different numbers, but that's not the end of the world. Science still goes on, because if we just got everything right away, we'd be out of a job, first of all. Things would be very boring if we got things right the first time. Why would we even do anything? So that's why this crisis is actually really fun. Okay, so I just wanted to leave off with these questions that that I asked at the very beginning. How do we know when we're right? And when do we say we actually understand everything? And this is a very philosophical question. This picture that I showed at the very beginning was a quote that was written on the board at the conference of this Hubble tension. And just from reading this, I think you can understand that everyone's having a fun time. Thank you.
So we're just going to get you to talk to the person sitting next to you about any of your questions so that we can give Victor a bit of a break, and then we'll come back and we'll ask Victor a couple of questions before we start our other activities this evening. All right?
Discrepancy be caused by measuring different parts of the universe. So my question is the expansion all the same speed in all the parts?
That's a very good question. So the question was, could the discrepancy be from the fact that we are observing different orientations or perspectives on the sky? My answer would be that there probably would be some sort of effect from that, but probably not too much. And I wouldn't be able to account for something like this, unless, of course, you would believe that we live in an exceedingly special place in the universe.
Is there any new hardware that's being used to maybe measure more precisely? I know there are abilities to do telescopes to orbit in space. Could one of those have some new tech that could allow more precise measurements and solve the issue?
Fantastic. So the question was, are there any new instruments or technologies that can help solve this issue with errors and understanding systematics? The answer is yes. That's why scientists are interested in this, is because they can research instruments and technology that can improve our measurements. I actually showed you a telescope earlier when I was talking about systematics. That was called the Gaia Telescope. It specializes in measuring parallaxes, and it measures the parallax of over 1 billion stars in our Milky Way, which is fantastic and enormously huge. And people studying the Milky Way are having a fantastic time with that right now. The problem with that right now is that there are systematic effects that are being studied that we don't understand quite as well, and it's an ongoing effort. As I say, people spend their entire PhD studying these kinds of systematics. So yeah, this is an ongoing work. I saw someone in the back earlier over there. I want to forget. Yes, over there in the corner.
Do you think discrepancy could be the result of us not knowing for sure what happened after Big Bang, and maybe the expansion rate was different at the beginning versus what we have right now? Because the expansion rate is changing, bottom line.
I see. So the question is, could the discrepancy be different because the expansion rate we measured earlier on is different from the expansion rate now? So I said the CMB measurement assumes that there is some expansion rate that evolves along with the universe, and we infer the Hubble Constant based on that and comparing the two apparent blobs that we compare. I think the answer is that that's very heavily tied into our theories that we think we understand very well. And to have our theories match the curve, the wiggly curve that I showed you, and also explain the formation of galaxies and stars is exceedingly hard. And to change that part, to make the measurements agree with each other is actually really hard, and that's what the theorists are trying to do, but I don't think it's very easy.
My question is, the size of the star, would that determine a change in the color? If it's larger, would it give a different color than a smaller one?
Okay, so the question is, do the sizes of stars determine the colors that we observe them at? Yes, so larger stars tend to be bluer than smaller stars, but that doesn't really play much of an effect into what I was talking about today, except that bluer stars tend to be blocked out by dust more than redder stars, but we know that and we know how to account for that as well. But that effect is going to be there forever. Lady at the front.
Like, as the years have gone by, last say 5, 10 years, if you have discrepancies in measurements, are they getting closer and closer?
That's a good question. So we've been measuring, so the question was that we've been measuring this Hubble Constant for decades now. Are the measurements getting closer and closer as our technology improves? Yes and no. So over time, these measurements have gotten closer and closer together, but lately they've been going further and further apart. While at the same time, we're improving our errors. So the extent of the area that they've been colored in has been shrinking and shrinking while they're moving further and further apart, which is actually very scary. And also very fun, because then we can start having fun with our theories and stuff. Yeah. Yes?
Why is the discrepancy considered such a big deal? Because if you look at statistics, even statistics governments give on non-controversial things like the number of students in the system, two different government agencies will give you two completely different numbers. They're close, but they're not the same. Now, both those numbers are in what I call the same ballpark. They both show it expanding. There's about maybe a 10% difference. Given all the explanation you did, which was very interesting as to why neither of them are actually accurate, is it surprising that they're different?
Yeah, that's a fantastic question and very well thought out, I think, of you. So the question is that, is it really that surprising that these measurements are so discrepant when, say, governments report statistics that are very wildly different, but you would expect them to be roughly in the same ballpark? And what I think what you're describing there with that is the error bars for those statistics are wide enough that they overlap with each other. These ones, we were saying that we understand them well enough that they should really be this number and this number. And that they should follow, they should obey the same physics that describe the origin and evolution of the universe. But that can't be true and also let you measure two independent numbers that are different. Measure the same number independently and get different answers. And I think that's the fundamental difference between the two things. I think you had your hand up.
Yeah. So like the latest things in astrophysics has been the development of like theory for dark energy, right? Do you think, I mean, my question is, are there studies regarding the Hubble constant discrepancy that take into account how dark energy could like affect the discrepancy?
Okay. So the question is, we know a lot about astrophysics, and things that we don't understand are things like dark matter and dark energy. Is there a possibility that as we understand more about dark energy, we can explain this Hubble constant discrepancy? I am not an expert on dark energy, but my initial answer would probably be no, because the theories that I said describing how we measure these Hubble constants take into account everything we know so far about these theories of dark energy and dark matter. Yeah. Right, last question. I'll take one from the back. Yeah.
That 6-point graph, where can I find more information on it?
The 6-point what?
The squiggly, the very
Power spectrum.
Oh, I see. So the question is, for the 6-number model describing the squiggly line, where can you find more information on that? I think it's great that you want to learn more. This is called the lambda CDM model of the universe. So lambda is a Greek letter. Looks like this. CDM. So if you Google that, you can learn about, this is what we call the standard model of cosmology. And it uses 6 numbers to describe everything we know about the origin and evolution of the universe. It doesn't describe everything perfectly, but it does it good enough that people tend to accept it.
Great. So just a couple quick announcements. If you have any more questions for